Okay, so I'll go ahead and get started. I want to say thanks again to the OU-Tulsa College of Arts and Sciences for sponsoring, coordinating the event, and Associate Dean Hellman, and also the OU-Tulsa Vice President for Research for also collaborating on and helping to provide the food and refreshments for today, and of course Shelley Fowler for helping set up the whole meeting room and coordinating, ordering the food, and all the wonderful things that she does. So thanks to all who were involved in helping to make this happen. So this is the second presentation of the research series on non-randomized designs going beyond randomized control trials. Yesterday we talked about non-randomized designs. Today we're going to talk about sampling strategies, and tomorrow we'll finish up by talking about the matching techniques for balanced designs, matching techniques that you can use in non-randomized designs. So we'll focus today specifically on the sampling and start with just kind of a broad general question, right? To think about, consider what can happen if you use an incorrect sample. Well, you have to know, what does that mean really? What is an incorrect sample? What do we mean by that? What are some of the possibilities of not using a correct sampling strategy? So just a little humor integrated into the presentation here. If you've got 3 people in your sample and you only take information from one, that's 67% of the responses, right? But it only accounts for a small portion of your sample. So you have to be concerned about, the non-response bias. So we're going to talk about some of the issues or considerations involved with sampling, different types of samples and sampling strategy. So just as a way to start, by definition, right, a sample is the next best thing to collecting data from the entire target population. A lot of times, we don't necessarily have access to the full target population. Many times we don't even know all of the characteristics of the target population because it's so large, it's unwieldy, and very difficult to even consider capturing data from the entire sample for a variety of reasons, just the difficulty of reaching them, not knowing who it is. But even if we did, in many cases, the population size is so large that it would be too costly to access all of the data or respondents in that population. So a sample is the logical next best thing to collecting data from the entire target population, but that means we have to take into consideration some very important issues. So there is this paradox of sampling. The idea of taking a sample from the population is that you want a sample that is as representative of the population as possible, right? The paradox, though, is that if you don't know the characteristics of the population, because you either don't have access to it or it's too large to know all of the profile characteristics of your population, how do you know whether or not your sample is representative or not? Right? How do you know your sample is representative of the population if you don't know the characteristics of the population? So the paradox is that we have to take a sample because we don't know the population. We want that sample to be representative, but we can't know whether the sample is really representative without knowing about the population. So that's the paradox. Well, we can resolve the paradox through a couple of ways. One is through incrementalism. We want to take many small samples from that population. So in incremental steps, we get small little pieces of the population, and cumulatively, we have a better sense of what that population really looks like, right? And we strive to obtain the best sample possible. Well, what does that mean? What's the best sample? What are the characteristics of a good sample? Well, the characteristics of a good sample really can be narrowed into 4 characteristics. We want a sample that is stable, we want a sample that is representative, and we want a sample that is random, right? So we're going to talk about how to achieve those characteristics within a sample. Another little piece of humor here in terms of getting the random sample and samples that are representative. So the character says, I just read your column in today's newspaper. How can you say that the number of functionally illiterate in our society is greatly exaggerated? And so he responds, I did a survey, and of all the people who completed and mailed back the questionnaire, no one was illiterate, right? So it's got an issue of sampling bias, right? It distorts your interpretation of the findings. Okay, so it brings up the issue then, the important issue for consideration, fundamental to sampling, is this distinction between probability and non-probability sampling, right? So non-probability sampling is when the sample is selected using some non-random process, meaning that it's not based on chance, right? Whereas a probability sample is one in which the participants are selected based on a random process, where random means that every person or every element in the population has an equal chance or equal probability of being selected, right? Everyone can be included in that. Okay, so just a little kind of heuristic for thinking about what this might look like. So, sometimes we ask, do we really need to measure everything? And of course, the answer is no. That's why we're taking the samples, right? But we want to do an adequate job of sampling. So we have the universe, which is the theoretical target population, everybody that we want to be able to generalize our findings to, and then the empirical target population of the individuals within that universe that we actually have access to or that we can actually contact, right? And sometimes this target population in some disciplines is referred to the sampling frame. Sociologists a lot of times refer to the sampling frame. So the sampling frame is that target population within the universe of everyone that we want to infer or generalize our findings to. But we've defined some parameters of that population. Well, then it's from that target population or that sampling frame from which we draw our samples. And so it could be that in a longitudinal study or in some types of study designs, you may have multiple samples from that target population that you take, preferably drawing at random those individuals. And so from that, you're going to have some probably dropout non-response rates or mortality rates, people dropping out of the study and things like that, which results in your final sample of data that you have collected that you can analyze and report findings on. Okay, so that's just in general what we think of in terms of the target population. We want, again, a sample that is random and stable and adequate. By adequate, we mean in terms of the size of the sample. It needs to be large enough that we can really make some inferences and generalize to that target population. So we have to ask some pretty important questions from the onset when we're designing our sampling plan, right? So who is it that we want to be able to generalize the findings to, right? Who is that large population, the target population, and what population can you get access to, right? What is it feasible in terms of the study population that you can actually access relative to that large theoretical population of interest, right? And then, of course, how can you get access to them? What is the sampling frame? What are the parameters? How do we define that before we go out and try to target that sample? And then ultimately, who's going to be included in your study? So there are many times important questions to ask about inclusion-exclusion criteria. Who needs to be included? Is language a factor, or is age a factor, or are there other demographic or profile characteristics that need to be taken into consideration for that ultimate sample that you plan to collect data from? So we'll start by talking about some of the non-probability sampling strategies. So non-probability sampling, again, is where we obtain the subjects or participants in the study in some non-random ways, typically volunteers, people who've just signed up for the study. They may be just available by accident or by convenience in many times. But ultimately, by definition, a non-probability sample is one in which all of the participants in that target population don't necessarily have the same equal chance or probability of being included, right? That's what makes it a non-probability sample. And so yes, question. The distinction between probability and non-probability?
Yeah.
Well, so one of the disadvantages of the non-probability sample is that we're limited in terms of the extent to which we know with any degree of certainty the representativeness of that sample relative to the population, right? That's the limitation of the non-probability sample. Is that what you're asking?
Yeah,
Or why do we have non-probability samples? Why would we even do that? So because I mean, in some cases, in some types of studies, it may be not feasible or not possible to take a random sample from the population, right? Or it may be that your study characteristics are such that it doesn't allow for that, right? So different types of non-probability samples that are available. This is, of course, not an exhaustive list, but some of the most commonly used non-probability sampling strategies that I'll talk about. The stratified disproportionate sample, or sometimes referred to as the stratified quota sample, most commonly, I think, probably just referred to as a quota sample, right? The same name refers to all of those: stratified disproportionate, stratified quota, or just simply a quota sample. And then the purposive or judgmental samples, another type of non-probability samples that I'll mention. The accidental sample, or the sample using the available subjects, sometimes referred to as a convenience sample, is another type of non-probability sample. And then finally, the snowball sample. Exactly. Non-probability, non-randomized are synonymous terms in the context of the conversation on sampling. That's right. Okay, so quota sampling. Just very quickly, the idea of quota sampling is you divide the population into the various categories of interest based usually on profile demographic type information. And then you determine the number of people that you need to select for each of those categories. It could be race or gender, it could be age, right? It could be, health status or something like that. But you identify what those categories are in the population and how many people from the population you need to include in your sample to be representative. So if 60% of the population is male, then maybe you, in your quota sample, you want to have 60% of your sample also male. It just means, as a non-probability sample, it means the males who ultimately end up in your sample were not selected at random, right? So for each of the categories that you identify as relevant or important for your study, you obtain an accidental or convenience sample until you fill the quota, right? So using the example of men, if there's 60% of men in the population of interest for your study, then you want to have 60% of your sample that also includes men, and you select those men in a non-random, convenient kind of way, take volunteers until you've met that quota. You can also, I've seen this before, where in quota sampling, they'll assign a weight to the respondents in a given cell according to the proportion in the total population. A lot of times that's done if you're not able to reach the quota with difficult segments within the population, difficult to reach, some groups of individuals or classes of individuals may be less likely to respond or participate. And so the responses that they do get, they'll assign a weight to those responses as a way to balance out that underrepresented segment in the sample. So this is an example of what a quota sampling strategy might look like. If we had a population, target population, so sampling frame of 15 elderly individuals living in a residential setting, and we knew in that population there were 1,500 females and 500 males, then our quota sample might contain 100 females and 50 males. So it's proportional to what that population looks like, right? It just means that those 100 females and 50 males were not necessarily included into our sample through random selection. All right, the next type of sampling strategy, the purposive, or sometimes referred to as a judgmental sample. This is when you select your sample on the basis of your knowledge of that population and its elements and its purpose of the study. So it could be very similar to a quota sample, but you could think of a purposive or judgmental sample as one in which you're looking for subject matter experts, right? So it's not so much based on demographic characteristics as it is on the qualifications or the knowledge or the skill of the individuals that you want to include in your sample. So you're intentional about your selection of those individuals into your sample because of some knowledge or skill that they have to contribute to your knowledge base. So an example might be if you're conducting a community needs assessment, right? And I think yesterday one of the examples I used was, if you're doing a study on homelessness, you have to operationally define what you mean by homeless. But if you're conducting a community needs assessment for the homeless population, it's a very difficult to reach population. It's very mobile. A lot of unknowns about that. And so it may be very difficult to collect data directly from homeless individuals, and there may be concerns about how representative that sample might be because of the limited knowledge about the population. So in addition to collecting information from homeless people themselves, you might also want to conduct a purposive or judgmental sample to also collect information from pastors of churches in communities or neighborhoods that have a high homeless population because of their familiarity with them through the services of programs that they provide through that church. So a pastor might be, a subject matter expert in that context. A local chapter leader of an AARP or an older person, maybe who's been living in the community for several years and is familiar with that, could also provide some insight into that population, even though they aren't necessarily fit the characteristics of the homeless population themselves. Okay, so just a couple of questions, research type questions in which you might use a purposive or judgmental sample, right? The homeless study might be one case. If you're interested in why some individuals who experience severe poverty and deprivation in childhood are successful as adults and others are not, it's also kind of a big, broad, difficult to reach population. And so finding individuals who have that experience or share that lived experience, those might be, subject matter experts, so to speak, that could provide some information about what you're interested in. Another example, if your question is why some women who experience a trauma, such as a rape, are devastated by the event, other people are able to rebound, more resilient, right? Then you may conduct a purposive or judgmental sample of individuals who've had those kinds of experiences, right? Then we also have the accidental or convenience sample, or sometimes referred to as an availability sample. This is probably the most common of all of the non-probability sampling strategies used, just the convenience sample, use of volunteers. We put an ad in the newspaper and include into our sample whoever happens to respond. Okay, so we're selecting people because they're readily available. We sample the members chosen because it's convenient, they're easy to access. So a lot of times, you go to the shopping mall or buy your groceries and somebody's in the parking lot with the clipboard and just, intercepting people on their way in or out of the store. Sometimes they refer to it as an intercept survey, right? That's a convenience sample. You just happen to be in the wrong place at the wrong time and you got trapped, right? So but we see this a lot, right? We see the reliance on these convenience samples quite a bit of the time. So several examples here of accidental samples where we place an ad in the newspaper, people who call in to volunteer to participate, or people working at a local senior center. So the sample, they take a sample from older people from that center, or people who belong to a particular organization, right? It's a captive audience. Right? We can do random sampling from a convenient list, and so it kind of enters into a gray area here as to, if we have a convenient list of employees at a particular organization, right, and we just happen to have access to that organization and we've got a list of those individuals, if we randomly select the individuals from that list, does that make it a random sample, or is that still a non-probability sample? It's kind of a gray area because, on the one hand, the original list is an availability sample in and of itself. So you can randomly select from that list. If it's a large list and you don't have the resources or the time to collect data from everyone there. But technically, it's still not a random sample in the sense that, depending on who your target population is, of course, if your interest is only to generalize your findings or results to that company, for example, then that company is your target population, right? You have access to the population data. If you're only interested in the individuals who are on that list, then you'd have no intention to generalize beyond that. Yeah, so in that case, you are randomly sampling from the population. Then it becomes then it is a probability sample, right? Because it increases your ability to generalize, right? You can be sure that your sample is representative of that population because you know who the population is. If, on the other hand, your interest really is in generalizing beyond just that company or beyond that list of names, then randomly selecting from that convenient list doesn't necessarily ensure representativeness of that larger population. Right? Okay, snowball sampling. This is kind of a fun, interesting one, and actually can be very useful. Snowball sampling can be very useful particularly for difficult to reach populations, where it's difficult to access individuals or members of the target population. So the idea of snowball sampling is you find someone who fits the criteria for the study, and then you take an accidental or convenience sample to obtain information from those individuals. You interview them or conduct the questionnaire or the survey, and then at the end of the interview, you ask the person if he or she knows other people who meet the study criteria and may be willing to participate. So this is what we probably all experienced with the telemarketing, right? They call you up and they want to offer you some vacation package, and if you're resilient enough to make it through all of their questions, then you get to the end and they want to know the names of all your friends and family members who you don't want to be your friends and family members anymore, so they can call them, right, and follow up and ask them the same question. So that's kind of how the snowball sampling works. But it can be a very effective strategy for difficult to reach populations, like the homeless population, and so on. And there are a variety of different ways to do the snowball sampling too, in terms of providing incentives and things like that. So if you're interested in conducting studies with difficult to reach populations, there's a whole literature on suggestions and recommendations on how to effectively use these snowball sampling techniques to work pretty effectively with that. Okay, where I really wanted to get to was the conversation on the probability sampling, because with a probability sample, it really does enhance the likelihood of getting a representative sample from your population. With the non-probability samples, you can never be certain. You can never be really confident how representative your sample is. With the probability sampling strategies, we can do that, right? We can be a little more certain or confident about that representativeness because due to the random sampling of the individuals from the population, it allows us to calculate sample error and confidence intervals around the individuals that are included in our sample, right? So because of the ability to talk about the sample error and confidence intervals, it increases our ability to talk about how representative that sample is. Obviously, anytime we take a sample from the population, there's going to be some discrepancy in the responses between the sample that we've obtained in that population, and that discrepancy between sample and population is what we refer to as sampling error, right? But it's only with the probability sampling strategies that we can calculate and be sure what that level or magnitude of sampling error is, right? So as an example, it's election season, election year, and so we see, on the news things about polling data, and you hear comments about, the plus or minus 3 margin of error, and we just kind of let that go and assume that the news people know what they're talking about. That margin of error is a reference to that sampling strategy. The margin of error is that discrepancy between the sample of the polling data in that context and the general population, right? And so in the last presidential election, we heard things like Obama has 52% of the vote in the polling data with the plus or minus 3 margin of error with a 95% confidence. So what that means, right, what that statement means is that if we were able to poll everyone who's a registered voter, then you're 95% confident that you would find somewhere between 49 and 55%. That's the plus and minus 3, right, of the 52. You're 95% confident you'd find somewhere between 49% and 55% of the population that favored Obama. So it gives you not just a point estimate of, it's 52% of the vote, but there's kind of a range of scores around that through which you can be 95% confident it's somewhere in that range. And the 95% confidence also determines, this is what's set by the researchers. You could be 90% confident, right? It's a broader range. Well, generally you'll see a lot of times the plus or minus 3 or sometimes a plus or minus 5. Yeah, it'll range, but usually it's not much more than that. If it gets too broad, then. Exactly. Yes, exactly. Okay, so I thought it'd be interesting to, since we are in an election season, to kind of update the slides and see, how does this look in kind of real world day to day. So on October 5th, right, this was a big date in the world of polling data because, as you might recall, it was close to October 5th that Donald Trump played the video with the hot mic on the bus. Yeah, the locker room talk. Yeah, thank you. Sorry. So these are data from Iowa, which is kind of one of the states to watch, right, where things are really close. So on October 5th, what the polling data for Iowa said is that Trump had 52% of the vote, Clinton had 48% of the vote, very close, plus or minus 3, with 95% confidence. So Trump's ahead. He's got more than half of the voters based on that day of polling, right? But we would still say that it's too close to call, right? Equally favored, even though it's over 50%. Why is that? Well, because the polling data was collected through random sampling strategy, right? It allows us to calculate these margin of errors and the confidence intervals. So even though what we observed directly was that Trump has 52% of the vote, based on what we know about the margin of error and our level of confidence, that means that we would expect, if we were able to collect data from everyone, right, that we'd find somewhere between 49 and 55% in favor of Trump, and 49 to 55, and 45% to 51% for Clinton, right? So it is possible, right, even though in our polling data, the direct observations, Trump has 52% of the vote, it's possible because of the margin of error that it could be 51 to 49 if we did it again, right? If we took another sample, it could switch. So we say, well, it's still too close to call, right? So that's why how the probability sampling helps us out. And these are data that I captured from the website there, which is really interesting. You can look state by state, right, of the polling data, not just for the presidential election, but for Senate races as well. Yeah, so what most of the polling, this is really sophisticated process now with the polling data. So in the old days, it used to be random digit dialing, right? And they would call up people on the phone, and then they realized, well, that's limited because not everybody has phones, and now it's limited because the random digit dialing doesn't necessarily provide known phone numbers to mobile phones, and so they use lots of different ways to collect the polling data now. So it's phone calls, they do internet surveys, email surveys. There's all kinds of ways. And it's a very competitive industry. I mean, these polling data people, these centers, they're like consultants, right, essentially. And there's a lot of them. And there's big money in this. And so it's very competitive in terms of who has the most accurate polls and are they consistent with the others. And, there's the Pew polls, and I mean, everybody's got a poll now. So it's a big deal. And they want to be certain. Nobody wants to say, well, here's what it looks like, in terms of how the election's going to turn out, and then it's completely wrong. Yeah, incremental in the sense that they're collecting polling data every day. They're updating. If you go to this website, or there's tons of websites you can go to, but this one's really interesting to me because they've got it day by day, from like back in the middle of June until today. You can see the track lines of what the polling data were, and they've calculated all these things. So it's really kind of interesting. So what happened on October 5th is we see these are the data. It's 52% to 48%, right? Too close to call. And then, they had the locker room talk, and it goes all over everywhere, viral. And then on October 6th, it switches, right? Now, same polling center, right? Just the reverse. Clinton had 51% of the vote. Trump has 49%. So it's that quick that you can see the switch. When the confidence intervals are, we've got a 95% confidence interval with the plus or minus 3 margin of error. And like I said, you can go state by state, and you can see in Iowa, the lines actually diverge pretty dramatically after that date. But if you go to Oklahoma, then what you see is this straight line from June until today. It's like 99.1% Trump, and straight line down at the bottom of 1% for Clinton, or 0.1. I think she doesn't even have 1% of the.
You said the numbers that we're looking at, the 51 and the 49, is that with the margin of error?
No, that's just the raw data, the observed data. So yeah, for all intents and purposes, still too close to call. But the point is that that's the reason it's too close to call. We know it's 3 plus or minus 3 with the margin of error, and the very next day it could reverse, right? When it's that close. Let's see. The margin of error is the same as sampling error. So it's like the standard error of the estimate. It's like a standard deviation, but a standard deviation, we're getting a statistical conversation here, but a standard deviation is the measure of dispersion or variability in the scores for a sample, right? Standard error is like the standard deviation of a sampling distribution, right? A sampling distribution of sample means where you've had multiple samples, theoretical distribution of multiple samples over time. So conceptually, it's the same thing, but it refers to a different kind of distribution of scores. So yeah, you can think of it as a standard deviation conceptually. Okay, so different types of probability samples that we can talk about. There's 3 that I think are really most important to talk about. Really, a lot of similarity between the first 2. A simple random sample is probably the most common of the probability sampling strategies that you see in the reported literature and studies that are done. Systematic random sample is very similar to a simple random sample. It's just got a few extra steps. And then the stratified random sample is really the only probability sample that provides you with a perfect microcosm of the population, right? It's really the ideal or gold standard of the probability sampling strategies, but it requires that you know some very specific information about the population in order to perform or conduct a stratified random sample. So we're gonna look at that one in a little more detail. So first is the simple random sample. This is where each person or each element in the population has an equal chance or probability of being selected in the sample. So here you get the joke already, right? So there's this person in the back that I can't hear you. Is it still random? Well, no, because they don't have an equal chance of being included in the study, right? So you get the idea. Simple random sample. You can think of it, it's like drawing names from a hat, or a lottery kind of approach, right? Everybody has an equal chance or probability of being selected. The systematic random sample is really just a little bit of an extension beyond that, where this is where you might have that list, right, from an organization, a list of employees or a list of students at a university, and from that list, you want to randomly select individuals at random to include in your study. And so what a systematic random sample does is it just chooses every K element in the list is chosen for inclusion into the sample. There are a lot of ways that you can go about doing this. K is the sampling interval. So if you have a population size, you divide that by how large you need your sample to be. Maybe that's based on resources or availability or time, or it could be a variety of different reasons. Statistical power analysis may inform what your sample size needs to be, right? So just for the sake of example, if you have a population with 200 people and you have resources available to sample 50 people from that population, then it's your population size divided by the sample size. So you're going to draw every fourth element from the list, right? Select every fourth person from the list to include, and then as your random location in the list. Or you select a random position in the list and then choose every fourth person from that, right? Not really that much different. I'm not sure that there's necessarily any advantage to doing that other than just having that systematic process for inclusion or selection into your study. Okay, so the stratified random sample, or sometimes referred to as a stratified proportionate sample, also sometimes referred to as a full probability sample, is, as I mentioned, the only probability sampling strategy that provides for you really a perfect microcosm of the population, a true representative. I mean, you can be certain with the stratified random sample that your sample is a perfect representation of that population. But it does have some requirements, right, which makes it difficult to perform, and which is why we don't see it very often. We don't see it done. Because in order to use the stratified random sampling strategy, you have to know the characteristics about the population. You have to know the relevant characteristics about the population, right? And the groups or the categories within your sample, similar to the quota sampling where you've identified the relevant groups or categories, those groups or categories have to be mutually exclusive, right? Mutually exclusive, so they wouldn't be in more than one group or one category. And you have homogeneous subparts, right? So comparable, I guess you could think of it that way, right? Comparable groups within your sample that provide the representation. We'll see examples of how this works, and I think it'll make much more sense. The purpose, of course, is to increase the probability of obtaining an accurate sample, a representative sample, by randomly selecting the participants from each of the significant elements, relevant elements from the population. And that, in doing so, increases the accuracy of your sample. So how do we do that? The first thing is you divide the population into two or more strata, similar to what we do with the quota sample, which is the non-probability strategy. So you divide the population into two or more strata, where strata is just a group of people who share some common characteristic. It could be race, it could be gender, it could be age, right? Something else. So marital status. From each of those identified stratum, then, a simple random sample is taken, right? And so you have these subsamples, really, from each of the stratum that are joined to form the total sample. But because you've arranged the sample or partitioned the sample by these stratum, these categories, and then you've randomly selected to fill those quotas, if you want to think of it that way, it allows you to ensure the confidence in the representativeness of the sample that you ultimately obtain. So here's how that might look. right? Example of a stratified random sample. If we've identified the relevant variables for our study to include race, gender, race, religion, education, income, and age. Those are the relevant variables that we need to include in our study. Then we have to operationally define, well, what do we mean by race? What do we mean by religion? What do we mean by, right? So that's where we define these attributes for each of those variables. So just to keep it simple for the sake of the example, we divide race into two categories. It's either a minority race or a majority race. And we have to further operationally define what exactly does that mean, right? Same thing with religion. We just have three attributes of religion: Catholic, Protestant, and Jew. For education, we may have high school, college educated, and then graduate or professional, right? That's how we're defining it for the purposes of our study. For income, we also have three attributes or three categories: low income, moderate income, and high income. Again, we'd have to further operationally define what does low income mean, right? What are the dividing lines? And then age, young and old. Again, we have to define what do we mean by young? What are the age ranges that define young age and distinguish it from old, right? So the researcher has to decide in advance what are the variables that are going to be stratified. We have to know the information in the population about those variables. We have to know the characteristics of the population according to those strata. And we want to keep the number of those stratification variables to a minimum, because otherwise the sample size requirements, the number of individuals that we need in each of those combined categories becomes difficult to achieve, and it becomes unwieldy, right? So we generally say the minimum number of strata is 10 cases, meaning in each of those categories. So essentially what we're saying here is we've identified the variables of interest, and we know what the relevant attributes for those variables, right? So then we're going to want to randomly sample from our population minorities who are Catholic, who have high school education, low income, and young. That's one group, right? And then we find minorities who are Catholic, high school educated, low income, and old. And that's another group, right? So we've got every combination of each of those attributes, right, in our sample. That's what makes it representative, because we'll go through each of those ordered combinations, right? So this is, already did that, right? Am I going backwards? Here we go. Okay, so how do we determine the number of strata? Okay, so we just build on our table. Here's the same variables, same attributes. So for race, there are two attributes, minority and majority. For religion, three attributes, Catholic, Protestant, and Jew. Education, three. Income has three, low, moderate, and high. And age has two attributes also. So to determine the number of strata, we multiply the number of attributes and then multiply that sum by a constant, 10, right, to get the total number of strata, right? So multiply the number of attributes, 2 times 3 times 3 times 3 times 2 gives us 108. That means if we create a little matrix for our sample, we got 108 little boxes that we got to fill for all the combinations of people that meet all possible combinations of those characteristics, right? So if we've got 108 little boxes, we multiply, that's our strata, we multiply that by 10 to get the number of individuals that we need in our sample at a minimum, right? So if we've got 108 boxes and we have at least 10 people in each of those boxes, it means our minimum sample size is 1,080 people, right? Make sense? It's a lot of details. It's very tedious, but the payoff is great, right? Because then you have a sample that gives you a representative representation of your population. So I put this on, this is the information, what I'm passing out is the information that's on the slide, but I couldn't get it big enough on the slide so that it wasn't blurry, so I just brought you a handout. Oh, sorry. So we'll go through this. This is an example of what the stratified random sample might look like in practice. So I just worked one out, right, as an example for you. So this is an example of or the population of interest, the target population, are 70 million US registered voters, okay? 70 million US voters in the presidential election, that's our population. Well, as it turns out, we have information, known information about that population, right? Because when people go to register to vote, we have other information about them, right? Driver's license number and things like that, which we can then use to find out, income levels and things like that. It's a government agency, so, we can find out anything we want to know. You report your political affiliation, yeah. No, you don't have to. You can register as Democrat and vote Republican.
Okay.
Yeah, there's no rules against that. It happens all the time, actually. Okay. All right, so we've got 70 million voters in our target population, about whom we know some of the characteristics, right? We have as our theoretically significant variables, they're the variables of interest, right? So before we had race and religion, education, income, right? For the purpose of this hypothetical study, we've determined that our variables of interest include sex, age, and income. So we have 3 variables, right? And so for sex, that's our variable. We have male and female are the attributes, so 2 attributes for that variable. Age, we've operationally defined as young, middle-aged, and old or aged, right? So 3 attributes. And we've defined roughly what each of those categories means. Young is 18 to 30, middle age is 31 to 60, and anybody over 60 is in the aged category. So two attributes for sex, 3 attributes for age, and then 2 attributes for income, poverty and non-poverty, where poverty means less than 15,000. So we multiply the number of attributes, so 2 times 3 times 2, that's 12. We multiply that by our constant of 100, gives us 120, right? So the minimum sample size, given those variables and the number of attributes based on the way that we've defined them, means our minimum sample size would be 120, right? So, because we're the federal government, we have enough money to, resources to have a larger sample than 120, we've artificially inflated our sample size to 2,000, right? So even though we need a minimum of 120, right, we're gonna increase our sample size to 2,000. Larger sample is, increases the likelihood of representativeness. Okay, so in our population of 70 million people, we have a sample size of 2,000. If we divide our sample size of 2,000 by the population size of 70 million voters, that gives us the sampling rate, right? The sampling rate is the sample size as a proportion of the population. So it's a really small number, 0.0000285. It's our sampling rate. Okay, so we can create a little matrix. I did this one in Microsoft Excel, right? Where we've got our 3 variables of interest, sex, age, and income, and we just nested, right? Sex is our highest level variable, males and females on each side of the table. And then within that, we have males who are young and poor, males who are young and rich, and so on. Every combination of those attributes for the variables of interest, right? And so then we randomly select from each of those categories the individuals to populate our sample based on what's known about the population, right? So the first 2 rows of data in our data table here is the known information from the population, right? These are the number in millions in the population by stratum. So remember, we've got 70 million registered US voters, and so what we know about that population of voters is that 4.2 million of them are poor young males, based on the way we've defined it, right? And 5.6 million of that 70 million are rich young males, and so on. So if you see across the row, we get our row total of 70 million, right? Which is reflective of our 70 million in the population. So this is just recording what's known, the known characteristics about the population, and then we transform those known raw numbers into proportions. So 6%, right? 4.2 million out of 70 million registered voters is 6% of the population, right? 6% of the population is poor young males. Well, if 6% of the population is poor young males, and we want a stratified random sample that includes poor young males, then we want our sample to include 6%, right? So if our sample size is 2,000, then we want 6% of 2,000 of the people in our sample to be poor young males. Well, 6% of 2,000 is 120. So we need 120 poor young males randomly selected from that population to represent that stratum of the population, right? And so we do that for each combination of these strata in the population, and then once we randomly select and fill each of those cells, right, we sum those up and we get, well, 1,995, right? Our sample size is 2,000. The reason I got 1,995, I did a little technique here, second technique, is due to rounding, right? So the numbers, not all of the numbers come up to whole numbers, right? You get decimal points and things like that. And I just rounded it up. And so, because you can't have, 0.34 of a person, right? So due to the rounding, we don't get the full 2,000 people. Not a problem though, because remember when we multiplied our 2 times 3 times 2, our minimum sample size requirement was 120. Well, so we're 5 off from our, inflated sample size, but we're still well over the minimum sample size required. So that, the fact that we're 5 off, 5 individuals short of the 2,000 that we aimed for isn't going to be a problem, because we only need a minimum of 120 people to be representative anyway, right? So we're fine. I followed a different little technique, and the rounding was a little bit different, and so I got the full 2,000 people represented in that sample, right? But the easiest way to do it, really, to determine the number of people that you need in each strata is just based on the known information from the population. If it's 6% poor young males, then it's just the 6%, 0.06, times 2,000 gives you the 120, and so forth across the table. So that's how you do a stratified random sample. It's tedious, right? It requires that you know very detailed information about the population, but the payoff is that you end up with a sample that is perfectly representative of the population of interest based on the variables that you've identified for the purposes of your study, right? So the payoff is great, but it does require that you know that information about the population. Then the bottom row is just by way of comparison what a quota sample might look like. So if you just chose, 6, you can use the same proportions in your quota sample. The difference, remember, is that in a quota sample, you're not randomly selecting those individuals for inclusion into your sample. You're just taking volunteers or something like that. But the way we would obtain these 120 individuals who are poor young males and 160 rich young males and so on is through that random sampling strategy, right? The lottery kind of approach for inclusion. So, questions or comments about that? Any questions? A true random, like a simple random sample, allows you to calculate those confidence intervals in the sampling error, the margin of error, but it still doesn't necessarily guarantee that you've got perfect representation. I mean, it does increase it, and it does allow you, at least what the sampling error is, but it's not quite as rigorous as that stratified random sampling strategy. Over several iterations of a simple random sample, right? Theoretically, it should play out. right? But most of the time, we don't have the time or the resources to conduct multiple random samples over long periods of time. Yeah, no, I mean, claiming it doesn't make it true, right? So yeah, it has to be known information. Usually, I mean, in this case, it was government archive data or public record, public information, something like that, census data.
So the source,
You go to the source. So if you're interested in conducting a study within a company, and that is your population, right? Human resource data provides that known population data for you, right? Within that company. It could be a very large company, with thousands of employees, and you don't have the resources to collect data from everyone in the company. You want to conduct or set up a stratified random sample, but based on human resource data information, because they're going to have all of that stuff, age, race, gender, probably, right? Income, those kinds of things. And so you could very easily identify what those proportions are in that population. Just an example. All right, thanks for your time.
Thank you.